Is our starting time, so we'll go ahead and get started. Thanks for joining today, you guys. My name is Amy Defoe. I'm one of the science teachers here at Graduation Alliance, and today we're going to be talking about science. Today's topic, we're going to be looking at plate tectonics. I've been doing some biology for the last couple of weeks, so let's switch it up and move over to earth science for this session today. Before we get started, we'll go over just a couple housekeeping items, just in case if this is your first live session, just so you know kind of how the sessions go. Today, I kind of put down there at the bottom of the screen, you can see the little agenda of how I'm going to lay out this hour, so you kind of can plan accordingly for that. So I'm going to start off talking, I'm going to give a little presentation about plate tectonics, and then we'll do our first round of questions. So you can see there it says 15 minutes questions. That's an opportunity for you if you have questions about a particular topic or a particular lesson or an activity that you're having some problems with, or you're struggling with, or you're not sure how to do, you can get that answered right here. And then I'll come back and I'm going to talk about some skills. I'm going to look at 2 activities that go along with plate tectonics, and we'll go over that. And then if we have some time at the end, I'm going to tie it in and talk about, why is science important to us? What's kind of the reason behind studying science and what we can get from it, and what it helps with us. It helps with us in our daily lives, if I can get my words out today, huh? So that's a little snapshot of what we're going to look at. And then, of course, I'll end the session with another question answer period so that you are set to go the rest of the week in science. These sessions are being recorded, so it's being recorded right now. We do that because we know, life happens. We've all got tons of responsibility, tons of things on our plate, and sometimes timing just doesn't work for us. And so if you're not able to get to a particular live session, you'll have the opportunity to see that recording later on at a time that works better for you. Also, we might go over something in the session that you think like, oh, that's cool. Yeah, I remember Amy, she went over something and I want to go back and review that. And so you can go back and see what it is that we talked about in this session here as well. And like I said, these recordings, we are creating this great library collection through all the different courses that we have here with Graduation Alliance on, there's activities in science and English, all the courses in which you can go back, and it's like this giant library of these sessions where you can go back and you can view the recordings at a later date. Because I know maybe you're not at plate tectonics right now, but maybe in 2 weeks you're going to be at that section, and so you'll be able to come back to these recordings and get some extra help and get some information. Okay, so I appreciate you guys joining today. You do have the opportunity to mute yourself, unmute yourself. I do encourage and I enjoy and I appreciate having that interaction in these live sessions. So if you have questions, you want to give feedback, you want to answer a question, because I'm going to ask you guys questions as well throughout the session, you can unmute yourself, you can just talk out loud. You can also use that chat box and you can type in any questions or answers, feedback that you might have in there. Kind of use whatever form of communication works best for you. If you do have some background noise going on around you, go ahead and mute yourself so it doesn't come in on the recording or distract others from the session today. But okay, again, this is what's great about these live sessions, is that we get to have this, we are an online school for the most part, but we get to have these opportunities in these live sessions where, we can see each other, we can hear each other, and we can have conversations and interact, which I think is important and I like to do. So please feel free to chime on in. Otherwise, let's go ahead and get started. Okay, so let's talk about plate tectonics. Hopefully in the background you can't hear the garbage trucks coming by on my street. So if you hear some loud banging, they'll be on their way here in just a moment. But okay, plate tectonics. So this is coming from earth science. So let's think about it. I always like to start start a topic by kind of thinking about, in the big picture, get our minds kind of plugging away at this. Has the earth always been the same? So as you think about it, our planet where we live, you could think about it lots of different ways. The surface area of it, the composition of gases, has it always been the same? Or does Earth change? So we're talking about plate tectonics. That might give you maybe a little clue that you're focusing in kind of on the surface of the Earth. Has our surface always been the same? You might not know. Maybe you do know. Maybe you have an idea. If you want to chime in a little response, you can. If not, I'm going to show you. Okay, so where does tectonic activity come from? So you're probably thinking, okay, we've got these words, we're talking about plate tectonics. Hey, welcome to the session. We're just getting started in on plate tectonics. So you're probably thinking, okay, plate tectonics, is she talking about dinner plates? What kind of plate is she talking about? As you're trying to maybe decode these words about what it is that we're talking about. Tectonic activity, what does she mean by that? I don't want to give too much away. So hopefully your mind is thinking a little bit about, the surface of the Earth. Is it always the same? Is it different? Let's move on. Okay. We're going to first start off by talking about the theory of continental drift. And you probably have seen this word or know this word, continent. So as you think about it, the surface of the Earth, as we're talking about kind of the geosphere, the lithosphere, the rocky substance that we live upon. We know, you probably remember back in history or geography class, you learned about the continents. And the Earth is made up of these giant land masses that we call continents. And there's a theory, so again, the theory here, there's evidence that supports the theory, but of course we can't call it a theory instead of a law because it hasn't been 100% proven. We can't be there seeing it. We can see it with evidence, little small parts of it. But as you think about the theory of continental drift, it's saying that over time, these continents that we live upon are slowly moving. And it came up with a scientist, you've maybe heard of this, Alfred Wegener. He proposed that the continents are moving. Now you're thinking, okay, I'm looking around here. I'm not seeing this movement happening. I'm not feeling it. Well, of course not. It's a very, very slow process that takes place here. And you might be thinking, no, there's no way, but I'm going to show you here today the evidence that helps support that this theory is actually true and that, the surface of the Earth is changing because it's moving. So again, we talk about these continents, and a continent, you might see, if you can see this light brown here, you probably know North America, the little light purple there, South America, those are two continents, okay? But then you see all these other colors that are there. And what those are plates. So think about the surface of the Earth. The rock that makes up that Earth, it's broken up into little pieces. So think about like a puzzle piece, okay? You can see as you look at them, they're not, uniform, nice little squares that piece in together. There's some jagged spots, but they all they come together as like a puzzle piece to make this nice surface of our Earth. So the plates are these giant slabs, pieces of rock, and they're slowly moving. So you're thinking about all these different colors that you see, those black lines outlining the boundaries. Those are what we call plate boundaries, where two plates come together. They're slowly moving. Now, when I think about that in my mind, I'm like, oh my gosh, what happens if you've got these giant slabs of rock that are moving? Do they all move in the same direction? Do they move in different directions? What happens when they run into each other? Okay, and that's what we're going to talk about with plate tectonics and tectonic activity, is what happens because of this movement. You can tell I like this topic. I think it's pretty interesting. So as we talk about Earth changing over time, now again, as you can see in this little picture here, we're talking millions and millions and millions and millions of years that this is taking place, that this takes place for these changes. The changes are very slow, but over millions of years, we see a difference in them. So maybe you've heard of Pangea before. And Pangea is this idea of a supercontinent. So at one point in time, all of the land masses on Earth, all the plates were, together. And slowly over time, they've shifted and moved apart from each other into the position that we see now. Okay, Have we been around for millions and millions of years? No. So where's the evidence to help support this idea? How can scientists say that this is happening? How do we know if we weren't there? And one of them is, Wagner, the scientist Alfred Wagner, he looked at, the continents. You look at a picture, a map of, of Earth, and you see the continents. If you were to put those together, they make like a puzzle piece. So it's like the fitting pieces of those continents in together helps kind of support it. As you can see here, as you think about it, if you've seen, you look at South America and Africa, if you were to squish those two together, it's like, wow, it's a puzzle right there. They fit together. It's like they're meant to be together. Okay. So looking at the globe, it reveals coincidences that are difficult to ignore, like that puzzle piece. The eastern coast of South America seems to fit perfectly, almost like a puzzle, into the western coast of Africa. At the same time, North America can be rotated slightly and made to fit comfortably next to Europe and Asia. So again, if you look at these continents, and if we just kind of move, because we know that the plates are moving, we don't know at all, if we were to churn them, so the direction that they move, North America kind of flipped up and, turned straight over long periods of time. But as you can see, they fit together like a nice puzzle piece. Kind of hard to ignore that. Okay, fossil evidence. So again, fossils are a great source of evidence in science, again, because they show us, the remains of life that was once living on Earth before our time. So fossils found on the east coast of Brazil, they match with the fossils found in Western South Africa. So again, looking at where those two continents fit together like a puzzle, we have similar organisms. The same fossils from the same type of organisms are found in those places. You can also see, you can look at it like India and Antarctica. Similar, same species, fossils found in both areas. Now you're thinking, okay, India and Antarctica, nowadays, you wouldn't think that the same organisms would be found in those areas. Tells you there must have been some movement happening, okay? Wagner noticed that a lot of the fossil life found in the rock didn't fit into the climates that they were found in. For example, rocks in Alaska contain fossil from palm tree leaves. Though there have not been any palm trees at that latitude far up north in the Arctic for a very long time. Pretty interesting. What else do we got? Surface changes. So with technology, we can see, how the Earth is changing. And what you're looking at here in this picture is, this is the mid-ocean ridge here. You heard that in the Atlantic Ocean, the mid-ocean ridge. And this is where new land is being formed. So this little red line that you see here, that's representing where that ridge is. And what it is, it's like an opening into the layers, deeper layers of the Earth. And what's happening here is that new land is being formed because we've got like a crack into the inside. And as you think about the layers of the Earth, inside we've got magma. So we've got hot molten Earth material that wants to escape because of this pressure. It's trying to get out. Well, here at this ridge, it has the opportunity to do so. And what's cool about this picture, you notice the colors. So this is millions of years, so it's looking at age. So we can look at, scientists can use technology and we can date the age of rock. So we can take a sample of a rock and we can determine how old it is. And these, where the red is, this is new land, new rock being formed. So we've got 0 million years ago. The oldest rocks being, that purplish pink color, 280. You can see a little bit of it right up there. So pretty cool to take a look at that, As you look at this ridge, and we've got another ridge here, you can see that, right at that ridge, we've got new, young rock. And on each sides of it, as it spreads out evenly, you can see the rocks getting older and older. So what that kind of looks like or shows us is that, we're getting new land coming up. That magma is reaching up to the surface. It's going to cool and harden, and it's pushing that land away from each other. So what this picture is showing is that the Atlantic Ocean is getting bigger. It's spreading apart, these two plates. Pretty cool, huh? We call this, this is called seafloor spreading, where we've got this ridge, this opening into the center, not the center, but into the deep layers of the earth. And we can see the seafloor is actually spreading apart very slowly as we're talking about it. Scientists like to say about 2 to 3 centimeters a year. But given millions of years, you get a big change. So thinking about how we went from that supercontinent of Pangaea to what we have now, there you go. Okay, so what happens because of plate tectonics? So because we've got these plates that are moving, is it perfect? You know, there's gotta be some, you know, effect to it. What are the outcomes of it? And that's, of course, is how we get earthquakes, volcanoes, mountain ridges, and that new land forming. Okay, so where 2 plate boundaries meet, we call that the plate boundary. 2 plates meet together. Again, that's called the plate boundary. Sorry, I want to make sure I get that piece in there. Some people are like, what? Plate boundaries? I don't get it. Where 2 plates meet together, there's a plate boundary. And how they interact with each other can give us a different type of an outcome. So there's really 3 ways that plates can move. The first one is what we call convergent, or a convergent plate boundary. That's going to be where our plates come together, where they like smash into each other. So think about rock being smashed into together. It's got to go upwards. Okay, so that's kind of how we get mountain ranges. Okay, divergent plate boundaries, that's that seafloor spreading. Divergent, if you diverge the ball, means you move out of the way, move away from it. So divergent plate boundaries, we've got plates that are spreading apart, and that's that seafloor spreading where we get new land. And the last way that plates can move is what we call transform plate boundaries. And that's where they don't move together, don't move apart, but they kind of move either side by side or what we would say side swipe each other. And if we've got 2 big old slabs of rock, you know, pushing on each other, trying to move and get past, when it finally moves and breaks, it releases a tremendous amount of energy, and that's an earthquake. Pretty cool to think about. Okay, so as we look at this picture, we can see the examples here. We've got convergent plate boundaries, again, where 2 plates are kind of coming together. We can sometimes get, with convergent plate boundaries, we can have different layers of the earth or different types of earth material. So you could have like an oceanic plate, or you can have a continental plate. And what's going to happen is one's denser, and so it kind of moves underneath and pushes upwards, creating these trenches, or in the area that I live, the Cascade Mountain Ranges. We call that kind of a subduction zone. Divergent plate boundaries, we can see right there. So think about that mid-ocean ridge, those ridges where there's this opening. Those 2 plates there, you can see they are moving away from each other. And we've got transform. Kind of hard to give an example of a transform, but I always like to use the examples we probably have all heard of, you know, the San Andreas Fault, California, around San Francisco area. We usually hear about lots of earthquake activity that happens there, and that's because we've got 2 plates that are trying to move kind of past each other. Okay, let's move on here. Have you heard of the Ring of Fire before? The Pacific Ring of Fire, more specifically? Well, if you look at this picture, we've got these yellow little circles. That represents earthquake activity. And this kind of orange one, even though it's kind of covered up by the other places, that's the plate boundary. And then we can see most of these kind of the red parts. You can see through here some of the island chains, mountain ranges. So this is showing us where the tectonic activity is happening. And this is the Pacific plate right here. And we've got North America, and we've got Asia. And what happens is we call this the Pacific Ring of Fire because if we look at where we have the most earthquake activity and volcanic activity, It's right along this ridge, or along this plate boundary. Okay, that's why we call it the Pacific Ring of Fire, because it's like a big old ring of tectonic activity that's given us volcanoes, lots of earthquake activity happening here. Okay, the reason is because that's where these plates are moving, and you can see that they're moving. That red, that's a convergent plate boundary where they're meeting together. Okay, transform boundary, you can see right there, that California San Andreas Fault one I was talking about. Again, they're trying to swipe each other, move by. Okay, so as you think about, well, where does most of the earthquakes happen, and where do we see most of the volcanoes? We call it the Pacific Ring of Fire because of those plate boundaries. So what makes this happen? How does, the earth, the plates, how do they move? And that's what we call convection currents is the reason for that. It's the driving force of plate tectonics. And convection currents, just like you've probably seen, maybe your stove, your oven at home is a convection oven. And what that means is heat cycling through. If you live in a 2-story house, think about the different floors that you could live on. First floor, second floor. Which floor tends to be warmer? As you think about heat rises up. So if you've got, multiple floors, the top floors are going to be warmer. So the same thing is happening inside of the earth. So as you think about within the layers of the earth, in the mantle here, we've got heat. So again, we know that the hottest is, the deeper we get is hotter. And as we move outwards, it gets colder. And the reason is because of that convection current. So this heat is rising, and as that heat is rising, it's mixing with cooler, denser earth material or the crust. And what happens is that heat rises up, and this is magma rising upwards, meets with this colder, denser material, and it cools. And as it cools, it slowly sinks back down, and it heats back up again. The heat rises, mixes with the colder, denser material, and it slowly rises back, sinks back down. And as it's moving and sinking back down, it's stretching those plates apart. So at that ridge, we've got new material that's able to escape out, pulling that plate, and then it moves back down into the earth and melts. Okay, so convection current, the driving force for plate tectonics. Why does this matter to us? Why do we care that the earth is changing, moving? Well, because we know that some of these events are, they can be damaging, not only to our planet, but to ourselves. As we think about, we hear about earthquakes happening and volcanic eruptions, and we've dying, other organisms dying as well, the atmosphere changing. Okay, so by knowing about this, we can prepare. We can think about what can we do? How can we, detect? Maybe scientists are working on technology to help us detect this. You've probably all seen, tsunami warnings, evacuation routes. So by knowing about these events that are going to happen, we can prepare and hopefully make them less of an impact onto us. Okay. I want to go back up to one other thing, because people like to say this, well, we can have activity, or we could have, say, like a volcano right in the middle of the ocean. So as you think about, if you've ever been to Hawaii maybe, or seen pictures of the Hawaiian island chain, it's not in the middle of, let me go back to this plate. So as you think about it, here's Hawaii right here in this picture of the Ring of Fire. It's right in the middle of a plate. And we talked about how tectonic activity takes place on these boundaries. Well, here's the exception. And that would be what we call a hot spot. So a hot spot is like a weak or a thin, we'll say, spot in a plate where magma is able to escape outwards and kind of erupt out, causing these island chains. Okay, and as you think about the Hawaiian island chains, well, why isn't there just one? Why is there many, and why do they kind of move in this nice little shape, arc? And that's because the plates are moving. So when that hot spot is active and there's an eruption that is occurring, that new land is forming, you know, maybe it dies down for a while, that plate moves. And so then the next island is developed when that hotspot becomes active again. So plate tectonic activity occurs where these plates meet together. The exception is a hotspot, where we have a weakening or a weak spot within a plate where it can break through to the surface. Okay. How are we doing? We doing okay so far? Okay. I wanted to look at, this is 431, Geologist Scrapbook. It kind of gives you a question, and all the questions are asking you is, they're asking you pretty much how an earthquake is formed, how a volcano formed. They want you to show that you can explain how each one of these tectonic activities is kind of taking place. Before we get to that, I did want to, let me see if I can, I'm going to show you guys a little demonstration here. Okay, can you guys see me bigger? Somebody want to give me a shake yes, or give me a yes, or type in yes. Can you see me bigger? I'm always so bad at this, you guys. Okay, I'm going to show you guys a little demonstration here. My candy's a little cold because it's a little cold here today. But what I want to show you is we think about, let's start here. As we think about, are you guys back on? We good? Everybody okay? Sounded like I lost you for a second. You got a shot. Okay, good. Thank you. Okay, I want to show a little demonstration. You can see me. Okay, so going back to here to this little demonstration here. There you guys, so you can see me, but not my screen. Hopefully you can see these tiles, okay? So we've got this red representing that magma. And I got two tiles here to kind of represent, you know, these two plates, okay? And we talk about, this is the outer layer of the earth. So we're looking at, you know, the crust, the upper part of the mantle, and the crust is what we're working with. And so when we think about a convergent plate boundary, we've got two plates, and what happens is they're moving together. So when two plates move together, you can kind of see what happens with these tiles. They squish upwards, forming those mountains, okay? And as we think about with a divergent plate boundary, those two plates moving away from each other, if we spread these plates away, what you see here in the middle, again, is that opening to that magma. So that magma is going to move up. It's going to fill in this line, this ridge, with new land, and that's going to continue to happen. And we're seafloor spreading here. We're pushing those plates away, okay? I also like to do, you think about, you can take little candies, and they can also help kind of explain those two together. So if you have two plates, and these two plates are converging together, they're going to push upwards. Again, like I said, sorry, my candy's not so warm. And they push upwards, and again, you can see little pieces break off. It doesn't look all uniform, gets a little jagged, but it's moving upwards, forming into those mountain ranges that we see, okay? Think about here, we have a Kit Kat. We think about a transform plate boundary where we've got a plate that side swipes or moves past each other. And again, when we get these plates where they meet at, there's so much energy that's there. And that release of energy is what these plates want to do. And that release of energy, or that break we get, is what we know of as an earthquake. So again, you think about it, when it breaks, pieces break off. So think about these two plates and they're trying to move past each other. And you know, you're gonna get pieces of rock that move offward, plates break. That break or release, sorry, kind of hard for you guys to see that, is what we feel as an earthquake. It's a release of that energy as they're finally able to move past each other. Okay. Let's see. Okay, so going over a couple of those questions as we think about, you know, an earthquake. What causes earthquakes and how are earthquakes measured? Of course, in the lesson, it goes over this a little bit more in depth, as I didn't talk about the Richter scale or anything, but earthquakes occur when two tectonic plates rub together along a fault, you know, side swiping or moving past each other. When the plate sticks, and then it suddenly becomes unstuck, it releases that surge of energy and it shakes the ground, and that's what we feel as an earthquake, okay? Earthquakes are measured by their magnitude, or that's the amplitude of the waves recorded on a seismograph. So a seismograph actually records kind of the movement or the vibrations that are taking place. And we use what we call the Richter scale. So you probably heard it was a 9.5 magnitude on the Richter scale. And that's kind of saying how much force is behind that earthquake, okay? So when we get something high like this, very, very devastating. Okay, what's interesting about earthquakes is they are occurring daily. They're in the lesson. There's a little website that you can go to, usgs.gov website, that actually shows you a map of current tectonic activity, current earthquakes that are happening. There's earthquakes on Earth every day. Some of them we don't feel. Some of them you might think it was, but it's pretty cool to look at it and be like, oh my gosh, I can see this. Hey, welcome. We're talking about plate tectonics. So it's pretty cool to see that this is actually happening. Okay. Volcanoes. What causes volcanoes to form? And then I asked you to give an example of a volcano. And in this lesson, it gave some historical examples of both earthquakes and eruptions that have taken place. So what causes volcanoes? Volcanoes form when magma works its way from the mantle through the crust and erupts, leaving ash lava deposits depending on what type of a volcano it is. So again, we come with two plates coming together, pushing up into those mountain ranges. Well, eventually you can get, you know, kind of like a cone or a magma chamber where that molten magma is trying to release that energy, and it does so with an eruption. This student gave an example of Kilauea, Hawaii, an active shield volcano. You maybe have heard of that one. I live here in Washington State, and right behind me is the Cascade Mountain Range, and probably another famous one that you've heard of is Mount St. Helens, the eruption of Mount St. Helens in 1980. Okay. Tectonic plate movement. What are plate boundaries? What types of boundaries are there? And what usually happens at each type of boundary? So again, we think about this in a bigger picture. Plate boundaries are where plates are meeting together, okay? Where two plates meet together, we have a boundary, plate boundary, okay? And there's three different ways that the plates can move. Convergent, divergent, or transform. Converge, so think about it, you're driving on a freeway, you're converging together, you're coming together, and that's going to produce mountain ranges, volcanoes. Divergent, you're moving away, that's seafloor spreading, we get new land. Transform, again, those plates are sideswiping or moving past, they release that energy when they break through each other. Okay, mountain building. So again, they say use the Himalayan mountains as an example, explain the process of mountain building that is caused by a plate. So if we go back to this picture here, Himalayan mountains, we can think about, we've got convergent plate boundaries. They're pushing together, pushing upwards, okay? What's cool about the Himalayan mountains is at the top of the mountain, and it's still growing because those plates are still converging, they're getting taller and taller and taller. Okay, Sorry, I went on and on because I love this topic of plate tectonics. So I apologize for going on about it, but I'm going to stop. And did you guys have any questions about plate tectonics, plate boundaries, or is there a lesson or an activity that you came to get some help on? This would be a great opportunity if you have questions. You can unmute yourself and talk out loud. You can chat in the little chat box if you would prefer to do that. Okay. I'm going to give you a little moment in case you're typing or thinking. Again, I will have another little question at the end where you can make sure to get your questions into. So if you're still thinking about it, you can think about it, and then we'll come back to questions again at the end. But, you know, again, with these live sessions, this is a great opportunity. You don't have to ask questions about plate tectonics. If you're working on biology and you have a question about the water cycle, you are more than feel free to ask that question, okay? You know, and as you're thinking about going through your courses and going through your activities, anytime that you feel like you're stuck on something, you're stuck on a question, you're stuck on a topic, it doesn't make sense, or you know, I've gotten this in a couple times in the last few days about, you know, I don't have PowerPoint. Is there another way that I can complete the assignment? And, you know, I'm totally willing, all your teachers, I'm sure, are willing to work with you and, you know, modify an assignment so that it, you know, fits the needs for you better. You just, you know, reach out, ask, make sure that you're, you know, kind of having these conversations and sharing us what is helpful for you if something would be better or not. Or if you're struggling on an assignment and you don't know what to do, or you're not getting that topic, ask away, send a chat, send an email. We're all here to support you guys. Okay, then I'm gonna go ahead and keep moving on here and we'll come back to questions. So I'm gonna go to activity 4.3.2, plate fact sheet. So what I do is kind of when I look at live sessions is I kind of look at, you know, the grade book overall, and I kind of look at, you know, averages, or look and see kind of what assignments students might be struggling with a little bit, and then I kind of like to go through with them. So this is one that I kind of saw as well. So the plate fact sheet. In this assignment, you'll show your understanding of the processes of plate tectonics and what we can learn from it. So the processes, that's looking at those outcomes: volcanoes, earthquakes, new seafloor. For this activity, imagine you're a geologist who works for the United States Geological Survey, that's that USGS. And as an employee, you sometimes take breaks from your fieldwork to answer questions from people who email you. Your boss has decided to put together a fact or a frequently asked questions sheet to put up on the website. This way, visitors can come to the website, quickly find answers to their questions, and guess who your boss wants to do it? You! So that's kind of the prompt or the idea behind this activity, okay? There's 6 questions that your boss wants you to answer. And here in the questions, it tells you to, you know, refer back. And there's a couple different units that go into plate tectonics because it kind of does everything that I just talked about, except for more in depth, okay? So as we think about, your first question is, how does the inner core affect all of the others Earth's layers? And I see this one, there's a couple in this activity that I see students struggling with. And this one, how does the inner core affect all the Earth's layers? This is a big one here. Well, the inner core is like an anchor. You know, the first layers, all the other layers kind of wrap around it. And it has intense heat and pressure, okay, that keeps that inner core solid, and the outer core is that fluid, and then the rest of the layers kind of slowly get cooler and cooler. So it's kind of moving this temperature out. The liquid outer core, composed mostly of iron and nickel, just like the solid inner core, generates a magnetic field that interacts with the inner core and dictates how fast it can spin. So these layers and this heat and pressure all create this magnetic field that we have here on Earth. You can think about how else you think about it, that's where that heat and pressure is coming from. That's keeping that convection current going, okay? But the biggest thing is it creates this magnetic field on Earth. What happens in areas where tectonic plates develop cracks in them? Okay, so just like we saw, you know, with the little candy bar pieces where we get cracks and breaks and you saw the little pieces of the candy fall. Well, that happens with plates as well. And these cracks are what we call fault lines. San Andreas Fault in San Francisco area, California, we talk about that very large fault line, and people can actually see these cracks in the earth, okay? Yeah, Denise, did you have a question? I had a hand raised. Denise, did you have a question? You wanna? Okay. If you have a question, you're welcome to chat in or just chime in if you want to talk out loud. Okay. Sometimes our buttons just get pushed sometimes because we're like, oh, oops, it happened. Oh. Okay, so these fault lines, that's where we get, you know, those cracks in the earth, okay? And that's where we have a transform plate boundary. Okay. What is gravity's role in plate tectonics? Gravity is the other main driver of plate tectonics besides convection currents. That's that process, the convection currents moving that heat around. With gravity, it's constantly putting pressure on the plates and pulling them, kind of pushing them down, pulling them apart, keeping them together. So it's kind of helping those plate boundaries move. So as we think about it, gravity's keeping everything on Earth down and together, squeezing them in, pulling it down. Oh, number 4, I love this question. If their inner core is so hot, the inner core of the Earth, the center of the Earth, if it's so hot, why isn't it molten rock? So you think about it. We've got the outside layer of the crust. That's the cool, harder outside rock layer. Then we have the mantle, which is the magma layer, a big giant layer of magma. And then we have the outer core, again, the same thing. It's a liquid layer. And then we have the inner core. And this inner core is a solid. It's the hottest layer. And it's like, wait a minute, how does that happen? Well, it's because there is so much pressure. You think about gravity pushing down. There's so much pressure in that inner core that the layers are so compressed, it becomes a solid, okay? So because of the immense pressure, it keeps the inner core a solid. And here's that hot spot question. Why do certain volcanoes develop in the middle of tectonic plates instead of between them near the boundaries? So again, we talk about plate tectonics. Where the plate boundaries meet is where we get tectonic activity, except with a hot spot. Okay, because in a hot spot, you know, in the middle, some tectonic plates, there's going to be weak spots where the rock is weaker, thinner layers, and it creates the ability for this heat and magma to kind of work its way out and escape. So as you think about it, as you have pressure, think about like, you know, a can of soda or a can of pop. It's pressurized inside and it wants to get out. Okay, so when you release that, like you flip the cap or you unscrew it, you're releasing that energy, that pressure, which is what it wants to do. It wants to escape out, kind of equalize everything out. The same thing is happening with Earth and inside the Earth and the layers. It all wants to get out, okay? So it's gonna find these weak spots, which we then call a hot spot, because that magma and that heat is gonna hit the surface. It's gonna release that energy. That magma eventually is gonna cool down. It's gonna form new land in the form of usually what we see, island chains like Hawaii. And the last question, this is a big one. What can we gain from knowing about the processes of plate tectonics and how it affects us? So again, going back to the question, why do we care? Why do we care that the Earth is moving and that some plates come together and move apart? Well, because like we talked about it, you know, Earth tells a story, a very, very long story, and we have to look at the past to Earth to kind of see what the present and future is going to happen. Earth has many cycles. So what happened in the past is most likely going to happen in the future. So we know that earthquakes are going to happen. We know that volcanoes are going to erupt. By knowing this, we can plan and we can help predict, and we can plan for the event that these do happen to lessen its impact on ourselves, our Earth and all the organisms that live here on Earth as well. So if you think about it, like I said, I live here in Washington State. We are due, so thinking about what we know from Earth's history, Washington is due for a pretty major earthquake to occur. And we also know that there are some volcanoes in the Cascade Mountain Range. And right now they're dormant, so they're not active. But knowing that and knowing where I live, it's like I want to know and be prepared in the event that they do become active again, or that there is showing some activity that an earthquake is going to occur. So, we can be prepared for it. Okay, any questions? Sorry, I could go on and on about this topic, you guys. I hope it's as interesting to you as it is to me. Okay, I'm gonna skip over this part, how does science relate to my life? And I wanna go to questions. I just wanna make sure if we do have any questions that those get answered first. Okay, as you think about these live sessions, and it's always great to come. If you do have questions with something, come to your session and get, firsthand, you'll get a question response right there. You'll get that interaction with your teacher. If you're talking about a science session with me or another session that you might go to. I always like to say also, if you're working on a part in your course right now and maybe it's a little confusing and you would like to see a live session done on it, if you have a suggestion for next week, I'll be back on Tuesday. If you have a suggestion for a topic, let me know. You can tell me here, you can send me a chat and an email. Hello, welcome. We're just talking about opening it up for questions. If you have any questions about any of the science courses or topics, you can get that answered. I always like to, ask my students if there's, what can I do to help? What would be a good session to do, a topic or an activity to go over, or a skill that you'd like to see some more work on. So always let me know. Any other questions? Okay, well, then I'm going to go back and talk a little bit more about science because, I've been teaching science for, oh gosh, about 17 years. And I always get a lot of students, the first thing, usually like the first day of class, it's like, I usually hear like, I love science, or I hear, I don't like science, or science isn't for me, or it's too hard, or it doesn't relate to my life. And I get it. But then I always want to say, but hey, let me show you how science relates to everybody. It is so much a part of our daily lives and we don't even realize it. Okay. Did I think that science was going to be, my career or my love or passion? I didn't, but it's something that does, parts of it, like earth science, does interest me. So I always like to talk to students about this, and in real terms, why is learning about science important? Okay. And I know for myself, I grew up in a family that traveled a lot, and usually, for the most part, we went on big trips, of course, and we would fly someplace cool, like a tropical island like Hawaii. But most of the time I grew up in the back of a pickup truck driving to wherever my dad wanted to go fishing. And back in that day, we didn't have, cell phones and laptops and iPads and everything like that. And so what did we do? I looked out the window and I looked at the scenery around me, and I would see, we would go from an area where we lived on the water, and then we would drive away and we'd be up in the mountains. And I would just always notice the changes of the surface of the earth, and always made me kind of think about it. Okay, so this is where I live now here in Washington. And this is the background here. This is what we're talking about of the Cascade Mountain Range, where we have those two convergent plate boundaries, the North American plate, the Pacific plate, and then there's a small little plate called the Juan de Fuca plate in there as well. And again, that's from that land pushing upwards. So people think about, do you like the mountains? Some people, we think about science and recreation. Okay, if you're a skier, snowboarder, a hiker, or one of my little kiddos, and you like to ride your bike down hills, we can think about you know, the different kind of landforms that we have, or topography that our Earth has, you know, it gives us so much recreation and things that we like to do and enjoy. So without plate tectonics, we wouldn't have these types of areas. In the winter, these of course are filled with snow. These are my kiddos in Hawaii a couple of years ago. So again, as you think about it, you know, they're out there playing in the ocean, and we talked about, you know, the water sphere with the water cycle, and we talked about a hot spot, thinking about how all these places occur. Okay, what about seasons, day and night? You know, why do we have, you know, winter, and then we have summertime? Sorry, I'm showing off my little kiddos here for you guys today, but I always like to show, you know, as we think about it, the way that the Earth is revolving or moving around the sun, and we've got this amazing little tilt that creates these seasons. I don't know how it is in your neck of the woods right now, but we are definitely in the thick of fall here, and all the trees are losing their leaves right now, and we're getting ready for winter. Oh. So you think about it, we just, for most of us, we changed our clocks back, and so now we're getting to that point where we're going to hit the shortest day of the year, and it's going to be dark. You know, learning about science and learning about the seasons creates that. Okay. I don't know if you guys remember, 2 summers ago we had an eclipse that happens here, and usually that occurs, you know, when the moon could get front behind of the sun, and you can see. So think about it, if you've never heard of an eclipse before, if you were in that Mayan civilization thousands of years ago, and you've never heard of an eclipse, you didn't have textbooks to tell you about it, and imagine this happens. How scary would that be? So kind of cool how science, we can make sense out of these ideas. We talked about, you know, for fun and transportation, you know, maybe you like to ride bikes, and maybe, oh my goodness, I bought a bike for my birthday last year, and ooh, I had no idea there were so many different types of metals that make one bike better than the other. And, you know, it's going along with technology, working on your game. I guess how fast do you want to go depends on what type of metal you want to get it. Transportation, you know, getting to see your family if you got to travel, going on vacations and whatnot. As we think about technology and science allows us to make travel a little bit more effective, affordable, easier to deal with. Okay. You know, think about other ways science influences us. You know, every day we are, you know, so in tune. You know, think about right now, we're in school right now, and here we are, we're using technology, we're talking to each other. This is face to face. You may be, you know, 2,000 miles away from me right now, but we're having a conversation right now, and that's science and technology, and it's going to continue to grow. So I think it's pretty cool to think about. We also know that we're dealing with topics like natural resources and global warming, and thinking about trying to preserve what we have and keep our planet as healthy as it can be. You know, that's another aspect of science. And of course, health, you know, keeping our bodies strong and well, and, you know, thinking about, learning about, you know, the foods that we consume, and medicines, and different kinds of screenings that now doctors use to help our, you know, detect things and keep us as healthy as we can. That all is science. So, okay. Sorry, I can go on and on. I like a science. So, does anybody have any questions? I just want to leave you guys with that, just thinking about it, because science is so important. And, you know, nobody's saying, there's parts of science where I'm like, oh no, that's too like geeky for me. Like, I have no idea. Like, when we come into parts of like chemistry, like my friends will always ask me questions like, you like chemistry and like physics? And I'm like, no, you know, there's parts of science that I really do love, and there's other parts of science that I can say, you know, definitely aren't for me too. So I'm sure I feel with you when you come and say, you know, I'm feeling I just don't like science or whatever, but I'm sure out of that little list I showed you, there was something interesting in there, or important to your life as well. Okay. Okay, so again, I will be on again next week. I know that there is a live session tomorrow with Jenna, another science teacher, and I'll be back on next week. If you have any questions in the meantime, you are free to please do email, chat, whatever your best mode of communication is, so you can get your question answered, okay? Otherwise, you guys, I hope I see you next week or hear that you're on the session tomorrow. Have a great day. Again, take care and thanks for joining. Bye.